All right, here we go. 1.5 is about a couple different things, parametric defined relations. These come up again in a lot more detail in semester 2, but we're just going to do some basic stuff with these in this unit. And then we're going to get into inverses. So we'll start with these parametric defined relations. So function, and specifically function notation, they're giving you y values in terms of x. You guys are used to this. Parametric defined relationships are going to give you x and y values in terms of the parameter, which is typically t. These are used a whole bunch in physics. Anybody taken physics before, or currently? You know the problems with the like baseball flying through the air. You had an x equation and a y equation, and they both had t's in them. Those are parametric equations. So that's exactly what this is. T is typically represents time in a parametric equation. All that fun stuff. Yeah. So you got to memorize. You know the parametric equations for what's that called? Projectile motion. Yeah. And we'll do that more in depth in chapter or semester 2. But for right now, here's what I need you to be able to do. Okay. If I give you a set of parametric equations, so our example here, notice it has 2 equations instead of one for the x and one for the y. If I give you a set of equations like this, I need you to be able to come up with coordinates for points and then graph it. So you guys remember back in Algebra 1 when you made those t-charts and you picked the x values and you plugged them in and you got y values and you graphed all those points? You guys remember doing that? This is going to be just like that. Instead of 2 columns, though, we'll have 3 columns. So we'll pick our t values and we'll plug them into both of the equations. So we're going to find x and y for t is -3. So to find my x value, it's just going to be t squared plus 1. And t is -3. So we'll simplify that. Can we do that in our head? What's that? 9 plus 1? 10? And let's find the y value. The y value is t plus 1. T is -3. We evaluate that, we get -2. So for a t value of -3, we come up with a point 10, -2. And let's graph that point on our graph here. So 10, 2, 3, 4, 5, 6, 7, 8, 9, 10, almost to the edge. Did I count that right? 8, 9, 10, and then down 2 will be right there. So we found our first point. All right, we'll just repeat the process here for -2, and then I'll show you how to do this on your calculator. -2 squared, that'd be 4 plus 1 is 5. -2, so -1. So 5, -1. If you get out your calculators, I'll show you the cheat code for this. Make this a lot easier on you. To graph these parametric equations, we need to put our calculator in a new mode that you probably have not used before. If you hit the mode button, the line you're looking for is function, parametric, polar, and sequence. So find that line, change it from function to parametric, and then hit y equals. And when you see y equals now, you've got a different set of, it looks different, right? For each of your graphs, you should have an x and a y. All right, so we're just going to type in our 2 equations for x1 and y1. The t button, when you're in parametric mode, is the same as the x button. That's why it says xt theta n. This is like your do it all graph button. So t squared plus 1 for my x and t plus 1 for my y. And if I'm looking to fill out this table, what am I going to do? We'll go look at the table. Yeah, second graph. And there we go. Let's see how we did. We plugged in, when we did -3, we got 10 and -2. Nice. And 5 and -1. All right, let's let the calculator do the rest of this for us. So I'm just copying these values off of my calculator. We got 2, 0, 1, 1, 2, 2, 5, 3, and 10, 4. And we'll graph those. Let me know if you have any calculator issues that I can help with. You guys, is it working for you? Did anybody try actually graphing it? And it kind of animates it for you, which is kind of neat. So if you hit the graph button, it'll actually animate it. Mine's got a little circle. Yours doesn't do that? All right, so if you go y equals and move your cursor over to the left of the first x and hit enter, you've got several different options there for what your line looks like. If you've got an older version of the calculator, just keep hitting enter and it'll cycle through. What you're looking for is a little bubble with a tail coming off of it. Yeah. And then when you graph it, then it should actually animate. Oh, yours is only doing the top part? I know how to fix that. Go to window. And yours is probably only doing the half of it because I bet your t min is at 0, is it? And we need to show some negative values of t in order to get our whole graph. So I made mine go from -5 to 5. Probably could have done -3 to 3. Anyways, let's just graph these points here, connect these dots, and move on with life. T step tells you like basically how long in between frames. It's almost like a frame rate. So the smaller you make it, the slower the object's going to move, but your curve will be smoother, if that makes sense. I have my t-step at 0.1. If you have it at 1 instead of 0.1, you're going to see like a jagged looking parabola rather than a smooth one. Okay. We'll spend a lot more time graphing these when we get into semester 2. For right now, the big thing is if you had to do it by hand without the calculator, would you feel confident plugging t values into a couple equations, coming up with a table, and then graphing them? If the answer is yes, then you're in good shape. Question? That's perfectly stated. The two equations are independent of each other. One of them gives you the x coordinate, the other one gives you the y coordinate, both of them in terms of t. Perfectly stated. All right. So it is possible to graph this thing or to write an equation for this thing that doesn't have t in it, which is what we're going to do next. What's going to happen though is we're going to lose some information. When we do these parametric equations, we look at these graphs, we're not just seeing the shape of the graph. When you animate it, you can actually tell which direction it's moving to. I'm going to put some little arrows in here to indicate that it's kind of started on the bottom half and finished up on the top half. So it's actually showing motion. What we're going to do here in a minute is eliminate the parameter. We're going to take these two equations, we're going to squish them together into a single equation that just has x's and y's. We're going to lose the t. And because we're losing t, we're not going to see that animation anymore. We'll just see the overall path of the thing. You guys ready to really pay close attention on this? I remember last year on the test, there's one question where we eliminate the parameter, and a lot of people really struggle with this. So put a star next to this. Make sure you come back and review this before our test. All right, so the steps are right there. We are going to take our two equations. We're going to pick one of them and solve it for t. We'll get t by itself. T will equal something, and we'll take that thing that t is equal to, we'll plug it into the other equation, and then we won't have any t's left. It's almost like substitution when you're solving a system of equations in algebra 1. So look at your two original equations and tell me which one does it look easier to isolate t in, the x equation or the y? We can pick either one of them, but I'm going with the y equation because that's way easier. So I'm starting with the y equation. Let me write it down here. Y equals t plus 1. And we'll do a little bit of algebra on that to get t by itself. So we'll do -1 on both sides. And we'll get y minus 1 is equal to t. All right, what are we going to do with that? Well, we're going to take our other equation then. My other equation was x equals t squared plus 1. But I left my t out. What am I going to replace my t with? We'll replace it with this y minus 1. Thank you. That'll give us x equals, let's go ahead and expand this out. Do you all know the shortcut for multiplying or squaring a binomial? So I'll give you a shortcut. We'll write it down here in a second, but you square the first thing and then leave a little space, and then I always square the last thing next. So -1 squared would be +1. And then you have to multiply the two things together and then double it. So what's y times -1 and then doubled? It would be -2y, and that goes in the middle. So square the first thing, square the last thing, multiply first times last and double it. That's my shortcut. So my final equation is x equals y squared minus 2y plus 2. All right, so we have eliminated the parameter. The parameter was t. We were able to take our two equations, combine them into a single equation, no more t. And if we were to graph this, and our calculator can't graph x equals equations, but if we were to graph this, we would see this sideways parabola. But what we would lose is that motion along the parabola. So any questions on that? Hey, do me a favor, up in the upper corner, we got a little space here, write this down. This is the shortcut I was just talking about. If you've got a binomial is something with two things, added or subtracted, doesn't matter, and you're squaring it, the shortcut is square the first thing, square the last thing, multiply them together and double it. It goes in the middle. Have you guys seen that shortcut before? We're going to use that a bunch in this class, so you can get familiar with that. It'll save you minutes of your life. While we are at it, this is another one that comes up pretty frequently, especially in the next chapter. You got it. You got it. All right. Oh, I forgot to answer a question here. Is this graph a function? No. It fails the vertical line test. Why don't you guys do this next one for me on your own? And use your calculator. Make it easy on yourself. Oh, can I borrow this? Can I put it on the screen? All right, so there's don't walk away though. So this is a common error that comes up. If you ever get a window range error, you're gonna go quit, look at your window. And usually it's because, like, if you've got a max and a min, usually it's because your like max and your min are either the same or your max is smaller than your min. So I look in T min and T max, 0 is less than 6, so that's good. Here we go, X min and X max. You see how you got 10 and 10 there? So you can't graph from 10 to 10. You wouldn't see anything. So I'm sure you meant negative 10 there. You might have accidentally just deleted that negative there. Yeah, thank you for that. That's a common error. Folks, again, when you get those weird errors when you're taking your test in a couple of weeks, you are welcome to ask me for help with errors. I'm not going to reteach you how to like find maxes and mins, but if you get an error, I will help you debug. Once you've graphed it, go ahead and try your hand at eliminating the parameter. When you do that eliminating the parameter, try and make life easy on yourself. Do the one that's like you add or subtract if that's available. Out of curiosity, how would this have gone if I eliminated the other way around? So y equals t. So y over 3 equals t. And x equals t is 2. Put in that y over 3. Good. X equals 1/3 y plus 2. I guess both of those would be acceptable answers. Did we end up with a function this time around? Yeah, that one passes the vertical line tests. All right, so just a quick introduction to these. Again, we're going to be using these a lot in, I believe it's chapter 6, second semester. But right now, if you feel confident, plug it in some values to get your x and y coordinates. I think what this looks like on the test is I give you a couple equations and I ask you to show by hand how you're going to find coordinates for a particular t value, kind of like we did up here. And then I will ask you to eliminate the parameter. And I had a lot of people last year. In fact, I had a lot of people tell me we didn't go over this. So you guys have seen it now, right? You put a star next to it, so you'll review that before our test. Awesome. All right, let's move on. You're doing great. Oh, I'm sorry. I meant to go down this way. Yeah.
It'll leave the way. I know it is nice to have those.
It is. Thank you. All right. You know what? Before we forget, why don't we stick our calculators back in the function mode? We won't be using parametric mode that much. So hit your mode button, put it back in function mode. All right. Okay, we're moving on to inverses. The big thing about inverses that you learned last year is what do inverses do to your x and y values? Yeah. So there's a geometric thing that's going on. There's a reflection across a particular line. But what happens to the coordinates? They swap. Yeah, the x and y swap. So So an inverse is literally just reversing a function machine. If you think about a function as something that has an input and spits something out, if you run it backwards, the output becomes the input becomes the output, right? So x becomes y becomes x. So here we go. Is this a function, this relation that I'm showing here? Yes. We're going to sketch the inverse. And the way we're going to do this is we're going to make note of the coordinates of each of these points, and then we'll just flip-flop the x and y coordinates. So this point here has coordinates 0, 1. If I flip those, I should get a point that's on the inverse relation. So that would be 1, 0. This point has coordinates 1, 2. So flip-flop those, you get 2, 1, which would be right here. And we'll do the last couple without labeling them. So what do we got here? 4, 3 is going to become 3, 4. 9, 4 is going to become 4, 9. And then we'll sketch that inverse in. Do you see some symmetry there? So it turns out you can do this graphically by reflecting over a particular line. Does anybody remember what the line is? Y equals x. Good for you guys. That's awesome. You had some great Algebra 2 teachers last year. So we can just reflect over the line y equals x, and I believe that's the last question in this section. All right, let's talk domain and range. So my original function, what was the domain of my original function? The smallest x value I'm seeing is 0, and it goes all the way off the right edge of the graph, so 0 to infinity. And the range of the original function, so what's the lowest y value that you see? 1, and then it goes up from there, and it's going to continue going up forever and ever, so 1 to infinity. What's going to happen to domain and range when we start looking at the inverse? They're going to flip, right? Inputs and outputs flip with inverses. So domain is just a list of all the possible inputs. Range is just a list of all the possible outputs. So it makes sense that they should flip. Look at this and see if that works. So does the domain end up being 1, infinity for the inverse? It does, yeah. And the range ends up being 0 to infinity. So I told you when we were in section 1.2 and you all were practicing that with that mid-unit review assignment on Monday, I told you for at that point, if I had asked you to find range, to just look at your calculator and give it your best guess. But now we have an algebraic way to find range, don't we? What's our method going to be for finding range? We'll find the inverse first, and then we'll find the domain of the inverse. That'll give us the range of the function. So moving forward, I need you to be able to find range algebraically also. We'll practice finding the inverse here in a moment, and we'll do just that. All right, let's talk about line tests. This came up, I can't remember if it was in this class or one of my other pre-calc classes, but we've heard about the vertical line test. The vertical line test tells us whether something is a function, right? What does the horizontal line test tell us? It tells us if the inverse is a function. All right, so let's do a little practice here. Our first graph, does this pass a vertical line test? No. So is it a function? No. Does it pass a horizontal line test? Yes, that means the inverse is a function. This next one looks like a sine graph to me. Is that a function? Is it a function? It is a function. It passes a vertical line test. So yes, it is a function. Is its inverse a function though? No. We're going to have to deal with that when we get into trig in the second semester. We're gonna do a little bit of math magic to make it a function. This looks like a cube root graph to me. Is it a function? Yup. Is its inverse a function? Yep, it passes both a horizontal and a vertical line test. And functions whose inverses are also functions, they're nice. It's a really nice property. We call those one-to-one. All right, so let's get into the nitty-gritty algebra piece of it. So we're going to practice finding the inverse function. Have you all seen this notation before? F inverse of x is how we pronounce that. It looks like an exponent of a little -1. Okay. So that's what we're going to use for the inverse. Anytime you see f with a little -1 exponent, that doesn't mean put it underneath 1 in a fraction. That means find the inverse of it. So we're going to practice taking a function, finding its inverse, and then analyzing domain and range of both the original and the inverse. So why don't we start by looking at this and talking about the domain and range of just the original function. This is a linear function, right? Domain's going to be what? Yeah, all real numbers. And the range, same? Okay. Well, then I'm guessing that the domain and range of the inverse are going to be exactly those two things as well. What should happen is we should see the range become the domain and the domain become the range. Those should match. All right, let's actually find it. So when we do this, we're going to think of f of x as y. So I'm going to write down y equals 2x plus 10. And then we're just going to swap the x and the y. Just switch places. So it becomes x equals 2y plus 10. And then we just take that and get y by itself. And that'll be our inverse. So solving for y, I would subtract 10 on both sides to get x minus 10 equals 2y. And then divide everything by 2. Bless you. And there we go. That's our inverse. Once we get y by itself, we'll just rewrite it. F inverse of x is x over 2 minus 5. Did our prediction hold up? Did we end up with the exact same domain and range for the inverse? It's another line, so it should have the same domain and range. Cool. All right. This next one, the algebra gets a little bit trickier. So stick with me on this, take some good notes, and I want you to stop me if you've got questions. Let's start out by looking at the original function and talking about the domain of the original function. So what are our problem areas here? No radicals, we have a fraction, right? That denominator could potentially give us problems. Let's go ahead and write down what the denominator is. And after it, please write the restriction. What's the restriction for the denominator of any fraction? Not equal to 0. We'll do a few steps of algebra and solve that. So the domain of the original function is going to be all real numbers except for -5/2. You guys feel comfortable putting that in interval notation? Give it a shot down here. You're going to have 2 intervals. It's basically -∞ to infinity. I'm sorry. Are you able to put a fraction in the calculator? In the interval? Yeah, sure. So that's the domain of our original function. Where is that going to appear over here? It should be the range of the inverse, right? So I already know that the range of my inverse is going to be -∞ to infinity, but excluding 5/2. -5/2. All right. Now, if we want to find the range of the original function, we're going to need to find the inverse, and then we'll find the domain of that inverse. So let's do our work to find the inverse. So my original function was y equals x minus 3/2x plus 5. We're just going to flip-flop it. Okay, so all the y's become x's. So this will become an x equals. Make sure you're replacing both of the x's over here with y's. I just said it, and I didn't follow my own instructions. See what I did? Oh man, that's an easy mistake to make. Classic. All right, so there's a process for solving this. We'll go through and kind of annotate it. So we did our swap. Next thing we're going to do is clear the fraction. I wouldn't normally write this down as a separate step, but since this is our notes, let's be thorough here. You guys know what I mean when I say clear the fraction? Yeah, I don't want a denominator here. How can I get rid of a denominator? You could multiply on both sides. If I'm tricky about what I multiply on both sides, I'll be able to cancel that denominator out. Let's multiply by 2y plus 5 on both sides. So that's going to cancel over here. We're going to be left with, let's go ahead and distribute that x. 2xy plus 5x. And over here, all we have left is the y minus 3 that was in our numerator. So we cleared the denominator in that second step. Feeling okay? All right. Now we need to get y by itself. We got y in 2 different places, and the real problem is we have y on 2 different sides of the equation. So my next step is going to be to collect all the y's on one side and all the x's, well, anything else on the other side. Okay, so I want all my y terms on, and I usually get it on the left. So I'm going to leave this 2xy here because it does have a y in it. I want this term on the other side, so I'll subtract y from both sides. And then this 5x, I'm going to get rid of it. I'm going to subtract it on the other side also. Now, I'm not showing my minus 5x on both sides. I'm not showing my minus y on both sides. Are you guys okay with kind of going between those steps without work? If it helps you to see the work, go ahead and squeeze that in. All right, so collect y's on one side. I'm hearing some questions. Maybe I need to show my work. So I wanted to get all my y's on one side. So I did minus y on both sides. And then I wanted to get rid of this 5x. So I did minus 5x on both sides. Ultimately, you want all of your y terms on one side, because that's what's going to allow you to factor out a y. So we want to get y by itself. There's y's in each of these terms. Let's factor a y out of that whole side. Running out of space here. What would we have left if we factored a y out of there? 2x, just 2x? Minus 1, good. Ooh, one more step and we got this. How are we going to get y by itself? We'll divide on both sides. So my step here was factor out a y. And then finally, we'll divide on both sides to get our final answer. So y equals negative 5x minus 3 over 2x minus 1. And that's going to be my inverse. So I'll write this up here. I want to give you a little warning here, but before I do that, what questions do you have about that process? Clear the fractions, collect the y's, factor the y out, divide. Okay, you'll do a few of these in your work, and I promise you we'll see one of these on our test too. Okay. Same format, same steps. I want to give you a quick warning because this is going to annoy some of you. There are a few different ways I can write this down. Okay. If you are doing an inverse in your assignment and you look up the answer in the back of the textbook, you would probably not see this answer. You would probably see this answer instead. 5x plus 3 over 1 minus 2x. That's probably the answer that you would see in the back. Let's not be taking pictures, please. Thank you. What are we doing to get from this to this? What did I do to the top of my fraction? I multiplied the top by a -1. And what did I multiply the bottom by? Also a -1. So I basically multiplied by -1 over -1 to get that other version. That's legal, right? That's just a fancy version of 1. So just be aware that when you go to look up your answer in the back of the book, if it doesn't match yours exactly, try multiplying the top and bottom by -1 in your answer and see if that matches up. Does that make sense? A lot of people freak out when they get to this section because they're like, I didn't do any of these right. And then I look at their work like, yeah, it's perfect. Both of those answers would be perfectly acceptable on a test. So, all right, let's wrap this up. Make a note that these are the same. And maybe just multiply by -1 over -1. We said we were trying to find the range of the original function. So let's talk about the domain of our inverse. So our inverse is here. To find my domain, I'm going to have to take my denominator, which is now 2x minus 1. And apply the restriction to it. It's the denominator of fraction, so it must be not equal to 0. Couple steps of algebra to get x by itself. And that's going to give us our domain for that inverse. But not only is that the domain of the inverse, it ends up being the range of the original. So we have now algebraically found the range of a function. It's kind of a long process because you got to find the inverse first. Yeah, you'll see a few of these. You'll want to practice a few of them. It's a lot of steps. Yep. So you're going to get used to this process where we collect a certain term on one side and factor that variable out. You're going to see this process pop up a lot in semester 1. Okay, actually semester 2. When we get into trig, we'll be seeing that too. So it's going to take you, you'll probably do 3 or 4 of these in your assignment. It'll take you a couple times through before you get kind of the flow of how to do it. The big thing I need you to know though is this. The key idea though is if I ask you to find an inverse, how do you find it? Swap the x's and y's and solve for y. That's the big thing. That's the big idea. The details here are that when you do that and you have a fraction, you're going to have to do these particular steps. Clear the fraction, get all your y's on one side, and then factor that y out. That's kind of the key piece for that. All right, you'll get a chance to practice a bunch of those. Let's move on. You guys are doing awesome. Last page. All right. This comes up. There's a little bit of a hitch in this, and it has to do with domain restrictions. So here's what I need you to know. Well, you know what? Let's not get into the details just yet. Let's practice what we just did. Okay. So let's find the inverse of this thing. So my original function is y equals square root of x plus 5. So if we follow those same steps that we did just a moment ago, we would start by, you guys just told me a moment ago, we just flip up the x's and y's. And then do a little bit of algebra to get y by itself. This one looks a little easier, right? We're not dealing with fractions here. So I'd probably start by squaring both sides. And then I get y by itself. Subtract 5 on both sides, and we got it. So according to my work, the inverse of f should be x squared minus 5. But there's a problem with that. So I want you to, once you get to that step there, see if you can figure out what the issue with that is. What do you think? Talk to the person next to you. See if you can figure out what the issue with that is. I'll give you a hint. You might want to sketch it. So are we seeing the problem? Graphically, do those two things look like inverses? No. I would say the original one is a function, right? The original one, actually, the inverse of the original is a function also. This inverse that I drew is not 1-to-1. It fails a horizontal line test. So how can we fix this? What do we do? What do we do to fix this? What do you think? Yeah, we just chop off the part we don't want. That's how we deal with this. So I'm just going to say, which half of the parabola should I keep? The right half. So let's just keep this right-hand side of it. And now it's an inverse. Now, in order to just keep that right-hand side, we got to add a little restriction on this. We're going to say f inverse of x is x squared minus 5, comma, but only when x is greater than or equal to 0. Yep. Okay. So, basically what I need you to do is when you're doing these, and anytime, this is only going to come up in this chapter right now, it's only going to come up when your function is some kind of square root function. You need to think about, okay, when I do that squaring thing, I'm going to end up with a parabola that's got both arms, but the square root only has one arm. So figure out, what do I need to chop off to keep it so that it works. There's going to be one of these on the test, and the problem that it's going to be on the test is going to have this little table on it. Okay, and you're going to be able to figure out whether you did it right, because if you forgot to chop that thing off, then your domains and your ranges aren't going to match up as they should. So that's kind of a built-in hint for you. All right. So, and this is going to be one of those things too. If you forgot to put this in here, you're getting 5 out of 6 points still. Okay, this is kind of a little detail, but we got to make sure that when we find an inverse, that the inverse matches up with the original function. Sometimes we got to chop some stuff off. Okay, we'll do this with sines and cosines when we do their inverses. That's how we deal with the fact that a sine graph, like we did here on the second page, does not have an inverse function. What we'll do is we'll just chop it off from here to here. And then that's going to allow us to take the inverse of it and have that be a function. More to come on that in chapter 7. All right. What questions do you guys have on this one? A little detail. Just worry about it when you got square roots. If you're what you would do on a test, if you can remember this, is graph your original function, graph your inverse, see if they match up with each other. If they don't, figure out, where do I need to chop that inverse so that it matches up to the original. Okay. Question.
So for that example you're just showing, to write that out as a problem, it would be like where you were just cutting off those sides, would be like x is like less than or equal to whatever on those sides.
Yep. Yeah, we would chop off a piece. Now with square roots, you're going to chop off like the left side or the right side. It's going to be x greater than or equal, or x less than or equal to. I'll show you some other notation if we're chopping off of both sides. We'll get into that later. Yeah, that won't come up until second semester though. Were there any other questions about this before we move on to our last one? Our last two? All right, verifying inverses. This is one of those things where you got to show me your steps. What was the other big thing that we talked about this chapter that I said, you've got to show me the steps in a particular way? You guys remember what that was? Even and odd. Yeah, good memory. Thank you. Yeah, you've got to start with f of negative x, and you got to end with f of x or negative f of x. This is going to be like that. Okay, I'll tell you that if you have two functions that are inverses of each other, all right, then if you do a composite on them, and if this works both ways, then you should come up with an answer of x. Okay, so here's kind of a visual way of looking at this. If I've got f and I've got f inverse, when I plug an input of x into this, I'm going to get an output of y, right? What if I were to take that y and plug it into the inverse? Remember, the inverse just does the exact reverse of the original function. Then I should get x out of the end of it. Okay, and it should work both ways. If I put x into this, I should get x out of that. So the way we're going to verify algebraically is we're going to practice doing these composites with these. And as long as we get x doing it both ways, then we should be good to go. So let's get started. This will give us a chance to practice what we were doing with composite functions a couple sections ago. So let's do f of g of x. And then we're just going to go through the same process that we did in the past section. Now, what's our answer going to come up to be if they are inverses? Actually, I'm telling you they're inverses. I'm asking you to verify that they are. What's my answer going to be? My final answer should come out to be x. Okay, but I need you to show me all the steps in between. Okay, you can't just like, and I'll have some students every year who will kind of just write a whole bunch of scribbles and then equals x at the end. And I'm like, yeah. So show me all your steps. So that means to take the g of x function and plug it into f. So g of x was cube root of x minus 2. How do we do that? Well, we take our f function and we're going to plug that big old mess into it. Let me write out what my f function was. It's x cubed plus 2. And then in place of the x, we'll put that cube root. Ooh, I think it's going to work. 2 more steps and we're there. All right, what's going to happen to this cube root in the cube? Cancel. We got x minus 2 plus 2, which is x. Check. We're halfway done. In order to verify, you have to do it both ways. So we need to now go back and do g of f of x. So try this one on your own. I'm going to work through it quietly up here, so feel free to glance up if you need a hint. But see if you can do it on your own. So with these, just make sure you're showing me steps. Show that substitution step. Show your simplification. Questions? Fair warning, this next one is messy. Okay. There's some real deal intense algebra here. I think it's pretty awesome. We'll see what you guys think. I'm going to write kind of small because it's going to take a little bit of work here. So we're going to do the same process here. We're going to do f of g of x. Some of you are looking at these two and starting to moan and groan because it looks like we're going to be plugging fractions into fractions, like in multiple spots. So we're going to end up with compound fractions, and this is a good opportunity for us to review what to do with that. So let's do it. So f of g of x, that's f of, what was g of x? 5x plus 3. 1 minus 2x. Let me get a little zoom going here. All right. My f function was x minus 3 over 2x plus 5. Double check and make sure I got that down right, and then I'll fill in the details. This would be the type of problem where some of my students would just go equals blah, 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 scribble X. All right. Time for us to talk about fancy ones. We're going to defeat this thing by multiplying it by a fancy one. Fancy ones. You guys learned about fancy ones last year? Yeah. Well, we multiplied by a fancy one earlier. We multiplied by -1 over -1. That's just a fancy version of one. Fancy ones, you know that you can take something and if you make a fraction and the numerator and the denominator are the same, it's equal to 1, right? Anything divided by itself is 1. So we're going to multiply this thing by a fancy 1. What would be nice to multiply this fraction by? 1 minus, if we multiply this fraction by 1 minus 2x, wouldn't that cancel out the denominator and we wouldn't have a fraction in there anymore? Same thing here. Why don't we multiply top and bottom by 1 minus 2x? That's legal. We're just multiplying by 1. It's a really fancy version of 1, but it is just 1. We'll be using lots of fancy ones in this class. I'm just going to write fancy 1. Have you guys heard of these before? What do you call them? I call them fancy ones. Fancy ones, and there's fancy zeros also, like -5 and +5. What's a fancy zero? Actually, basically all of algebra is multiplying by fancy ones and adding fancy zeros. That's how you solve equations. All boils down to that. Anyways, okay, now we got to be careful about how we do this because this is going to distribute. It's going to multiply both by the 3 and by the fraction, okay? This is going to multiply both by the 5 and by the fraction. So this isn't bad. You just got to keep track of what's going on here, okay? It gets messy, but it's not impossible. So when I multiply the 1 minus 2x by the fraction, it's going to cancel the denominator. We'll just have the 5x plus 3 left over there. And then when I multiply it by the -3, I'm actually going to write it out here. 1 minus 2x. Now this step I might skip if I were doing this in an assignment. All right, when I multiply in the denominator here, the 2 is going to stay. I'm going to multiply the 1 minus 2x times my fraction. That's going to cancel my denominator. So I've got a 5x plus 3. And then multiply the 5 by it also, which is going to give me my 1 minus 2x there. You don't like it? I'm sorry. But this is where it gets exciting because it's going to end up being x. It's going to be awesome. All right, let's keep going. A little distribution up top here. What do we got? That's just 5x plus 3, and then be careful with your negatives. That's -3 and plus 6x. Does that sound right? I'm just distributing up here. Distributing on the bottom, we got 10x. 2 times 3 is 6. And then I got 5 times 1, so plus 5. 5 times -2x is minus 10x. Ooh, this is where it starts getting fun. You see those terms are about to cancel out? This is tingling. So excited. All right. The 3 and the -3 are canceling. What do we got left up top? 11x, that's all that's left. And on the bottom, the 10x and the -10x are going to cancel. So on the bottom, we just have 11. Hey! Oh, that was awesome. That was so fun. And we're halfway done. We got to go back and do it the other way, right? Which I didn't leave myself room to do. Oh, so many complaints, so many complaints. It's all right. You guys got this. You got this. Here, let's do it the other way. I'll race you. Anybody want to race me? Come on. Be bold. Be bold. On your marks. Get set. Go. No way. Well, yes, we know that it equals X, but show me your work. Oh no. What did I? Oh, I messed the sign up. This is a minus. Sloppy mistakes slowed me down. Done. Anybody beat me? Beat me, nice. That's all right. That's great. It's kind of messy. Folks, we're going to be dealing with bigger messes than this in this class, so it's time for us to just kind of put on our big kid pants and deal with it. Sometimes it gets messy. My favorite kind of messy is where it starts out messy and then it simplifies down to something nice and simple like X. So, all right, that's about as bad as it gets algebra wise in this chapter. Cool. All right. I'm not going away. Just stopping the recording.